All right, looking at Ka and pKa, to start with, remember from a previous video I said there's a table in your book, table 2.1, that you need to have memorized. Memorize this table of pKa values. It, in my opinion, is one of the big keys to understanding organic chemistry. The students that really understand organic chemistry have this table memorized because a little hint, a little foreshadowing. Although this gives us pKa's, which tells us about the Bronsted-Lowry strength of acids and bases, it turns out that the Lewis strength, Lewis acid-base strength, parallels this, and all organic reactions are can be classified as Lewis acid-base reactions. So if you know this table, you will understand your organic reactions much better. Memorize this table. But in the meantime, let's go on and talk about what this table means. All right. So, acid-base strength, Ka and pKa. Recall Gen Chem 2 here. Gen Chem 1, HA, an acid, plus water will be in equilibrium with H3O plus A minus. Base, here's its conjugate acid, acid its conjugate base. And you can write the expression for the Ka, the equilibrium constant expression for this acid reaction. Ka equals a concentration of H3O plus times concentration of A minus products over reactants, concentration of HA. Recall water is a liquid, so it is not in Ka equations. All right. So recall for CH3COOH, Ka is like 1.76 times 10 to the minus 5. Recall that pKa is the negative log of Ka. The reason is we hate numbers like 1.6 times 10 to the negative 5. You calculate the pKa, and it's a negative log of that 1.6 times 10 to the negative 5, you get 4.75. I would much prefer to use numbers like 4.7 than 1.7 times 10 to the negative fifth. We don't like using all these exponents. Much easier to remember 4.75. Okay. Here's the deal. The larger the pKa value, the weaker the acid is. Remember, pKa is the negative log. So the larger this number is, means the more negative this number is. Times 10 to the negative fifth. Times 10 to the negative 10th gives us a larger pKa value. Larger the pKa, the weaker the acid. So CH3COOH has a pKa of 4.75. We call that a weak acid. CF3COOH has a pKa of 0. So this is a smaller pKa value, therefore a stronger acid. Larger pKa equals weaker acid. Smaller pKa equals stronger acid. So CF3COOH is a stronger acid than CH3COOH. HCl, pKa is negative 7. That's even smaller pK value. So this is what we, strong acid. It's much stronger than this one and that one. More negative pKa means a much smaller pKa. The smaller the pKa, the stronger the acid is. All right. So, one thing that gets confusing with organic chemistry, when we deal with water, we note that the Ka for water, concentration of H3, water dissociates, would be H3O plus times concentration of OH minus. It would be Ka, but in organic chemistry, we put the water in there. Okay. We have the water as part of the equation. So the pKa for water is not Kw. Remember, Kw for water is 1 times 10 to the minus 14th. pKw would be 14. The pKa for water is 15.7. The reason being, in a lot of our organic reactions, we're going to generate water, or water is going to be part of the reaction, but water is not the solvent. Our stuff doesn't dissolve in water. So if water is not the solvent, then we need to include it in our Ka equation. All right. So the truth is that if we have HA plus H3O plus goes to H3O plus A minus, KEQ, the equilibrium constant, the concentration of H3O plus times concentration of A minus, divided by the concentration of HA times the concentration of H2O, which is 55.5, and that's a constant. And so we find out that when we include that 55.5 in there, that the pKa of water is 15.7. And we need that number of 15.7, not the pKw of 14, to understand our organic reactions. All right. So, very important part right here, predicting the strength of bases. The stronger the acid, the weaker its conjugate base. Recall, we get the conjugate base of an acid by removing a proton. You remove a proton from HCl, you get its Cl base, or its conjugate base, Cl minus. You remove a proton from CH3COOH, you get CH3COO minus, its conjugate base. The stronger the acid, the weaker its conjugate base is going to be. Therefore, the larger the pKa, recall the larger the pKa, the weaker the acid is. The weaker the acid, the stronger the conjugate base. So if you see large pKa values in that table, we know those are weak acids, which means their conjugate bases are strong conjugate bases. Okay. Which tells us that OH minus is going to be a strong base, because let's look at the conjugate acids from whence these came. OH minus, the conjugate acid, well, if this is the base, how do you get the conjugate acid? You add a proton. So you add a proton to OH minus to get the conjugate acid, that's H2O. You add a proton to CH3COO minus to get its conjugate acid, that is CH3COOH. Add a proton to Cl minus, its conjugate acid is HCl. All right. Another way to look at it, we've looked at the conjugate acid of OH minus as H2O. Another way to look at it is OH minus is the conjugate base of H2O. But then we look at our pKa values. Water, what's the pKa of water? Oh, that's right, that's 15.7. CH3COOH, the pKa, oh, that's 4.74. HCl, the pKa, oh, that's right, that's -7. HCl, pKa -7, very small number. The smaller the pKa, the stronger the acid. The stronger the acid, the weaker its conjugate base. Cl minus, very weak conjugate base. H2O, pKa is 15.7, which means H2O is a pretty darn weak acid. That's a very weak acid because it's got a fairly decent large pKa value. 15.7 large pKa value, which means the larger the pKa value, the weaker the acid. The weaker the acid, the stronger its conjugate base, hydroxide. That can be a little bit confusing. Straighten it out in your head. When you see large pKa values, we know that thing is a weak acid, but we also know if you took a proton away from it, it would have a very strong conjugate base. If we go back to our table in the book, at table 2.1, what we see is here are our acids, and note we noted that H2O, here's water, is a very weak acid, but it's towards the top in terms of increasing acidity. pK 15.7, we know the conjugate base, hydroxide, is a strong base. All of these other molecules have pKa's larger than water. If these pKa's are larger than water, that means all of these guys are weaker acids. These are weaker acids than water, which means these conjugate bases are all stronger conjugate bases than hydroxide. And that's going to be important in organic chemistry. Earlier on in previous video, we said hydroxide is the strongest base that can exist in water. Hey, guess what? Water is probably not going to be our solvent in these reactions. Therefore, we can get these super strong conjugate bases. These bases here are extremely strong, and we can make them because we're not going to have water around. If you put any of these guys in water, they would immediately react with water to form OH minus. Because OH minus is the strongest base that can exist in water, and these guys are all stronger than OH minus. However, without water around, we can have these very, very strong bases. Also note while you're memorizing this table that although we have some specific compounds here, these are representing general class. Any alkane, any hydrogen bonded to an sp3 hybridized carbon, pKa of 50. We'll break that rule in organic too, but we won't worry about it. A hydrogen on a carbon that's part of a double bond, alkene hydrogens are 44. Any alkyne, a terminal alkyne, doesn't matter what else is on here. There could be a bunch of CH2s on here, and then this terminal alkyne, pK of 25. This was designed to represent all alcohols. Alcohols have pKa of 16, very similar to water, but in general a little bit less acidic than water. And the more stuff you have on here, the more shrubbery you have on this oxygen, the more carbons and hydrogens over here, the larger this gets, 16 to about 18 or so. And CH3CO2H represents any carboxylic acid. As long as it's a normal alkane bonded to a carboxylic acid, pK is about 4.8. So when you're looking at these tables, these are the general molecules. Don't just look at the exact specific molecule of acetic acid. Look at all carboxylic acids. This molecule is acetylene. Don't just look at acetylene here. Look at all terminal alkynes. Okay. So now that we know all this and we have that table memorized, hint, hint, exam coming up, we can look at some trends here. Let's look at predicting the outcome of acid-base reactions. And note, I've just put my pKa table down here, the one from the book. Recall H3O plus is 1.7. I just copied the book table. We need that H3O plus. Let's just slam it right in here because this is where it belongs. H3O plus negative 1.7 for its pKa. We got to have that guy in there. The fact that it's missing from your table is a crying shame. Okay, so turns out we can predict the outcome of acid-base reactions as long as we have this table memorized. And this video is getting a little long, so let's end here and we will continue predicting the outcomes of acid-base reactions and going through some examples in the next video.